Oops, I'm sorry about that, students. I had an alarm set that I should have turned off, and I didn't. Anyways, it interrupted my phone and my recording. So let's see. Let me pick up where I had left off. I kept talking there for a while, but you can see then for number 8, I punched in A for the correct answer, and so we were working here, and we were saying right here that when you calculate this, be careful with the negative. That's the tricky part. But anyways, then when you do your calculation, you get a negative 2.7. So definitely nearsighted. That's what the negative means. And reasonably nearsighted, not too extreme, but still enough. And that's my prescription. So that's kind of how I know. All right, let's go on to the rest of the exam, and hopefully no more alarms will interrupt us here. All right, so more on our optics. This is our last chapter on optics. I think this is 22. It says, what is the first order diffraction for orange? And it gives us the wavelength. That must be shine on a diffraction gradient, and it gives us the number of lines per millimeter, and it gives us some different angles. All right, so number 9 here. Let me write d sine theta equals to m lambda. And this was our equation, if you will, for the diffraction gradient, where the d is the distance between each line, and then the angle is where the light separates out. This is the wavelength, and this is which order we're looking at. So in this case, it says first order, so I can put m equal to 1. It says it's orange light, so I will put 595, and then I'll do nanometers. Maybe the tricky part here is the D, because this is listed as 250 lines per millimeter. And maybe I'll write that as millimeter. So if I just get my calculator out and go 250 and divide it by 10 to the minus 3, we're looking at 2.50 times 10 to the, let's see, that should be 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5 lines in 1 meter. And so now if I take the reciprocal of that, I get the amount of meters per line. And that's what I need here. That's what D is, the distance between each of them. So let me hit the reciprocal key and come up with 4 times 10 to the negative 6 meters between each of the slits, each of the lines. And so 4 times 10 to the minus 6 would go here. And then, of course, now I've got some mathematics to do in order to solve this. Now, let me just check the mode of my calculator. I'm in degrees because I'm looking at solving this for the angle, and I see that my answer options are all in degrees. So I just want to double check that. All right, so on this side of the equation, I will put the 595 times 10 to the minus 9, and I will divide that, and I'll do last answer. And so that should be the sine of theta, and then taking the arc sine of that, we're looking at about an 8.55 degrees. And so if we had the light coming in and we had this diffraction gradient, there would be the main beam right there, but then off at an angle of 8.55 degrees would be this orange color. And I hope that's one of my options here for number 9. Let's see, number 9. Yeah, it looks like C is my option there. Okay, good. All right, and then let's go to the last of the multiple choice. Here we have polarizing light with an intensity of 225 watts per square meter, traveling through a polarizing filter, reducing the intensity down to 10 watts, like viewing the great... yeah, I hope you took some time to watch the eclipse. I guess that was 2 days ago here, but it was amazing. And I was glad I traveled out to see it. In fact, in passing here, I'll just say, put that on your bucket list. Everybody should see it. I've been wanting to see one my whole life, and finally, 6 decades later, I'm here. I actually saw it. So it was worth the effort here. All right. In fact, I'm ready to get on a plane and return home real soon here. But I wanted to wrap this up before I go. All right, what is the angle between? And so this is what I was doing, is I was filtering the sun and the intensity, and had some polarizing sheets and some UV filters and whatnot, but I can look then at the eclipse. And in this case, I'm going to use the equation that says if you take the original intensity and you multiply it by cosine squared of the angle between them, you get a reduced and smaller intensity on the other side. So the math here is to make the intensity on the other side down to 10, and it's 225 coming in and already polarized. In my case, that's because it went through the UV filter first, and that polarized it and reduced the intensity. And so then when it gets to the next filter, which this is kind of what I was thinking in the math, it's the next filter is going to reduce that down. So I'm going to reduce it down to 10. Anyways, and so this would be cosine squared of some angle. So I guess the first thing to do is a little bit of math that says, let's go 10 divided by 225, and that would be cosine squared. Let me then take the square root of that, and I'll pause there at 0.2108. And so that's the cosine of the angle. So then I can go arc cosine and get an angle of 77.8 degrees. And so sure enough, then our last of our multiple choice, there it is, 77.8 degrees. And so that would be answer D there. Okay, nice. All right, well, I hope those went well for you. Now let's move to the second half of the exam, and that is question 11, where we have our free response. All right, let's see. Let me get my paper ready here. But I will call this 11A. Maybe I need to make this a little bigger on my screen. And I'll kind of move it up here. But it says, an engineer builds a simple radio based on an RCL or RLC circuit. And it has this capacitor of 1.22 nano capacitance and a 50 ohm resistor. And then it has a variable inductor that we can connect in series. So our standard power supply, standard circuit diagram, and then it's going to have this variable, which then we can tune to make it the accepting or the resonant frequency. And so the first part is supposed to be the easy part. The main part is really coming in B, but it just says draw a schematic diagram showing this circuit and label the components. And so what we would have is our three objects in series. It doesn't matter what order you put them in. And since we call this an RLC circuit, why don't I just do the resistor first? Then I'll do the inductor. And this is the one that's going to be variable, so that's what the little arrowhead is. That's something new to you. That's what this problem's kind of describing. And then the capacitor. And I'll put capacitor, inductor, resistor. And so hopefully you have something that looked like this. And so if you were trying to either transmit or receive, you might then, put this up on a long wire. This is your antenna, if you will. And so what happens is the antenna catches all these radio waves, but what actually gets through is then something that depends on the L and the C, okay? So anyways, it says here, label the components, and this is fine. An R, an L, and a C work fine, okay? Now, they do give me some values. Let me just put them in here. But the L is the one that allows me to tune it. And so I can pick out different frequencies. And that's really what B is all about. And so this is A, where A is, hey, let's go ahead and just draw the circuit. But B is to do this calculation. It says to listen to the radio station. So we're trying to pick up a frequency of 91.9 megahertz. Okay, and that's what it says here. The circuit is to be tuned for a resonant frequency of 91.92. What value of the inductance should be set? Well, hopefully you just kind of remembered our discussion that the magical frequency, the resonant frequency, and this would be the angular frequency, so it equals to 2 pi f. That's another little tricky part here. But this is the magical frequency. Now, if you forgot that, maybe you remembered this, that the current following Ohm's law for an AC circuit is voltage divided by the impedance. And the impedance is the square root of R squared plus XL minus XC squared. And since the impedance is in the denominator, you're going to get your most current, that is, the wave that passes through here. The one that gets the most current would be the one where XL and XC are equal. And so this is the reactance. And so this is 1 over omega C, and this is omega L. And so if you've forgotten this, you can hopefully just come back to the fundamental idea of our current and get this frequency. And of course, what we're trying to do is we're trying to say, okay, if I'm trying to tune it, I would probably be doing some kind of adjustment, either digital or by hand, and I would then turn, maybe I'll just call it an old-fashioned by hand knob, adjusting the inductance until I got the correct value of the inductance. And so I'm going to go ahead and square both sides. So I have 1 over LC, and when I square a 2, I get a 4. When I square a pi, I get a pi squared, and I get then an F squared. Now, if I rearrange this, maybe I'll take the L and move it over to the right, because that's what I'm trying to solve for. And then I will leave my C over here, but I'll also put together the 4 pi squared and the F squared. And so this is how I'm going to get my L. Now, So now I can grab my calculator here and say, okay, let's go ahead and multiply these out. Now it said that the capacitance was 1.22 in nano, and then times a 4, and then times a pi squared, and then times a frequency of 91.9 to the 6th and squared. I'll just hit enter right now. And so that would be everything along the denominator there. So let me take the reciprocal of that. And it looks like I get 2.46. And it says times 10 to the minus 9. So I'll write that as a nano, and inductance is in henries. And so this should work. That is, if we adjust the inductance to be 2.46 nanohenries together with this capacitor, it would have an impedance that then minimizes the impedance and then maximizes the current that flows through this circuit. And that's why we call this a tuning circuit. Anyways, this is the main equation right there. So I hope you recognize that one, because this can be a hard problem there. All right, so hope that went well for you. Let's move on to the next one, which I guess would be 11B. All right, so 11B, I think, takes us into our optics. Oh, yeah, and kind of a challenging one here, because we need to look at two lenses. And so this is a lot harder than the multiple choice one here. But the hint down here says for a two-lens system like this, the image of the first one becomes the object of the second one. And so what we're going to do is make a compound microscope, and it has 12 millimeter focal length for the objective lens and a 64 millimeter focal length for the eyepiece. The objective and eyepiece are then separated by 18.2 centimeters, and the scientist places the species or specimen of which now becomes the object under the microscope to view it. And I know this can be a hard one, so I go, well, if I put the image from the book, maybe this will help you guys. And so let me put this near the top of the screen here, and then just write out the two main equations. So that is 1 over the object distance plus 1 over the image distance is 1 over the focal length. But let me also split my paper in half, because I need to do this a second time, because I will call this first column right here, you know, what's going on for the first lens, which was the objective lens. And that's the one that is close to what we're trying to examine. And then the second set of equations is the optics that is taking place for the eyepiece. Okay? And let's see what we have here. And so a compound microscope has a focal length of 12 millimeter focal length for the objective. So right here, and let's see, I guess I have to make a decision here about what units to use, because this is in millimeters and this is in millimeters, but the separation is in centimeters. Maybe this will be a little unconventional, but why don't I do everything in millimeters instead of converting things to meters? That way, I only have to convert this one to millimeters. So that would be 182 millimeters. I think I'll take that approach. All right, so right here, the compound microscope has a 12 millimeter focal objective piece. So this would be 1/12 right there. And then over here, let's see, the eyepiece, a 64 millimeter focal length of the eyepiece. Okay. So that's the information they give me from the starting, using, of course, the hint of doing this equation twice. I may just make that a solid line. Okay. Now, here it says, if the final image appears to be 55.8 centimeters, oh, let me be careful there, I'm going to use millimeters, behind the eye lens, where is the specimen? And so they're looking for this. What is the distance of the object from the objective lens? But what they're giving me is the final image. And so that would be the image distance of the eyepiece. So this would be 558. And like our other optics one, be careful with your sign, and you can kind of see it here a little better in the picture. Here's the eye looking through the eyepiece, and it sees a virtual, very large, upside down image. Of course, you guys have probably used microscopes a lot. That's one thing that always was challenging for me, who doesn't use a microscope very much, is every time I get my eye in a microscope and I go, oh, I want to look down a little bit, I move it. The slide, I go, oh, I want to look down, so I move it up, thinking I'm going to see it, and it's the wrong way. It's like, oh, no, wrong way, because everything is reversed. Anyways, so the final image is actually magnified by a lot, and it's inverted, but it's also virtual. And so there's that negative number that we have to be really careful with. And you see, that's enough information right there to allow us to solve for what is the object distance. So, keeping that in mind, I'll grab my calculator here, and I think I'll take that as a 64 and a reciprocal. And then imagine moving that to the other side, so it becomes plus 55. Oh, is it 558 or? Yeah, 558. Okay. And 558, and then I'll forget reciprocal when I bring it to the other side. And if I hit enter, and then the reciprocal of that, we have an object distance of 57.4, and let me just remind you, in millimeters. Maybe now I'm regretting doing everything in millimeters. Because what that would mean, coming to our picture here, is that this object distance, which, by the way, maybe I should put little primes here to indicate the second one, because that's how the diagram has it. I have just solved for this right here. And this is saying then that the object for the eyepiece right here is 5.74 centimeters, or 57.4 millimeters. That's this one here. Okay. So with that in mind, I could then figure out how far this, which is the object of the eyepiece, and it's the image of the objective piece. And so they told me in here that the distance separating these two lenses would be let me just call it L, 182 millimeters. And so my point is, if the distance between these two lenses is 182 millimeters, and this distance is 57.4, I can then subtract those two and find out the image distance. So let me do that. Let me then take 182 and subtract 57.4. So 182 minus 57.4, and we're looking at 124.6 millimeters for this distance, which, remember, is now going to be the image distance that is created from this first lens. So I'm kind of working things backwards. And so that is kind of hard also. Now, again, let's pause for a moment and say, okay, would this be a positive or a negative number? Because again, the math isn't too bad. It's just this formula that we got to do twice. That's what makes it hard. And we got to connect the two. That's why we got to do that subtraction. But now I have to say then, is this a positive or is this a negative number? And coming back from the picture, we can see that this is forming a real image from the first lens. And so this is a positive number. And so sure enough, I put it in as a positive number. And now I can get the object distance from the objective lens, and that's what A is asking. And so let me take here, which is the reciprocal of 12, and if you imagine moving this to the other side, I'm going to subtract off the 124.8 reciprocal, so it's when I get to the other side. If I hit enter, that's the reciprocal. So finally, taking the reciprocal, we're looking at 13.3 millimeters for the distance that the object is from the objective lens. And so in our picture, that would be this right here. So that was kind of a long problem. Oh, no, we're not done. There's a part B, but we got enough information to answer part B. But we just simply did all this math backwards, but we got to watch our signs. Okay, so we got positive for the two focal lengths, and we got negative for that objective distance, and positive for that one. And that could be the tricky one. Oh, and connecting the two lenses together to figure out how you get the object of, the image of the first becomes the object of the second. And then we got to do that in reverse order. But I do like my answer. I mean, if you check this out, we do see that it's kind of like that multiple choice one where we had the projection screen. We knew that the object had to be just a little bit greater than the focal length, and that's what we see here. It's a little bit greater than the focal length. And so we have to be greater than the focal length, but the closer we are to the focal length, the larger the magnification. So that's how we want to have this. We want to have the specimen that we're examining just a hair more than the focal length. And so 13.3 is just a hair more. It's only 1 millimeter, 0.3 bigger or further away than the focal length. So that works out nice. All right, so now back to the question. I think what we've answered is just A. If the final image appears to be blah, 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 where is the specimen? Okay, so we got that. Now, over here, what is the overall magnification? Well, we've got enough information to answer that one because we can have magnification from the first lens and magnification from the second lens. So this would be minus the image distance over the object distance, and this would be minus the image distance, and I'll put a prime for the second lens, the eyepiece lens, and over the object distance of, again, the second piece, the eyepiece. So using these numbers, it looks like we have a negative 124.6, which we get from right here for the image distance, and the object distance is 13.3. And then for number 2, the image distance we said was a negative 558. So with the first negative and the second negative for the distance, that makes 2 positives. And then the object distance is the 57.4. Okay, so our first magnification would be a negative 124.6 divided by 13.3. And that would be a negative 9.37. And our second magnification would be 558 divided by 57.4. And then that's a positive 9.72. So the total magnification is the negative 9.37 times the positive 9.72, which overall then gives me a negative magnification of negative 91.1. Yay! All right. So that was a pretty hard one too. So hopefully you did well on that. I'll have to keep in mind and be pretty generous here with these negative signs, because I have a feeling a lot of you did the logic real sound, but maybe messed up a minus sign. And that's not a real big deal. Obviously, I'll dock off a few points for it, but you might have gotten some really bizarre numbers. But notice the negative, and so it's upside down. And notice it's all because of the first lens. The first lens turns it upside down, and the second one makes it bigger but keeps it upside down, as again shown in the picture here. It clearly shows the image of the first lens upside down, and then that one is getting bigger but remaining upside down. All right, then on to our last one, another optics one, and this is maybe the easier of the three. I'll let you decide that, but it's again got its 2 parts, so it's kind of long here. And the first part, much easier than the second part, and that's again because reflection is much easier than refraction. So here it says a ray of light hits a mirror and the incident angle, call it angle I, is 37.5 degrees. How much is the ray deviated? So in other words, the engineer or the scientist in some way wants to redirect this ray, and so they want to bend it. In this case, if you kind of imagine you were traveling with the ray coming this way, you would say, okay, I'm going to bend to my left by some angle which is called delta. And so you are going, okay, what is this deviation angle? Using the lowercase delta as the kind of the universal standard for what we call deviation angle. And so we're controlling our optics. And so we're, an optical engineer, we're processing the light, we're trying to bend it in a certain direction. Hopefully what you see right away is the angle I plus the angle R plus the deviation angle makes a full 180 degrees. Because we are told that this incident angle is 37.5. And hopefully also you know the law of reflection says that you get the same angle in reflection as you get incidented. And so the math here is pretty straightforward at this point then, that says, okay, I'll take 180 and subtract a 37.5 and another 37.5 and get 105. And so the deviation angle for 11C, part A, would be 105 degrees. Now B is a little bit harder because it uses the law of refraction, but I also tried to set it up so that it's actually fairly easy to do. And we do have some refraction, and we have it twice. And so let me talk about the bending of the light as it enters the glass. And so as it enters the glass, I need to draw a normal because I need this angle here, which is 45 degrees. That's the incident angle. And hopefully you see that because the picture shows this as 45 degrees and a normal, is at a right angle to the surface. And so these two have to add up. And so they're both 45. Now, maybe you could have gotten lucky, and if you use this as the incident angle, it's still 45. So I guess in one sense, I'll never know if you made the correct connection. But if you did that, it'll probably haunt you later on because this is going to bend towards the normal. We learned that the light, when it comes in, bends towards the normal. And of course, this would be the angle that we would find based on Snell's law. So let's do the law of refraction, Snell's law, and calculate what this angle in here would be. I'm going to call it theta 2. And so we start in air, which has an index of 1, and we have a sine of 45 degrees, and we're going into this prism. It's probably lead glass prism because it has a high index of 1.65. And then we can find our angle theta 2. And so grabbing my calculator, I will go sine of 45. I will then divide that by 1.65, and that should give me the sine of theta 2. So then I will take the arc sine and get 25.4. And of course, the reason that's important is because that tells me how much it already bent. So remember, here's the normal, and here's straight through. That would have been 45 degrees, and so this whole thing here would have been 45 degrees. So if I take 45 and I subtract that, this angle right here, the amount of bending it did at the first interface, is going to be 9.6. Okay? And that's where it's real important that you recognize which one here is this refracted angle. And so the one you solved for, 25.8, isn't the one it bent from. And you might do that if you messed up this 45. All right, so I'd say that's half the problem. How much it's bent already. And it looks like if you were like traveling along this ray, you'd say the ray is bent to the right by 19.6. Okay, well, I'm going to let this continue to go out. And here's where I kind of set it up easily. You don't really need this amount it bent the first time, because watch this. In the second part, now I'm going to draw this back wall here of the prism. Oh, by the way, if I didn't make that clear, this right here was supposed to be the entering face of the prism, right here along the hypotenuse of this right triangle. And now I'm trying to draw this vertical leg here. And so the light is approaching. And And so here is this light beam continuing to hit the back one right here. And if I draw a normal, the normal will be horizontal. And since it's exiting, it's going to bend away from the normal. And like I said, I set it up in kind of an easier fashion, because then this right here is the angle from the normal. That's what we're going to be calculating from. But it is also the angle from horizontal, which is then the deviation angle. Because remember, the original ray is coming here straight in. And that's why I made the comment that we really don't even need this 19.6. This just tells us how much did it bend as it entered. And we could then say, okay, it's going to bend some more, and the two added together is the total bend. But it turns out this right here is going to be both the total angle it bends, it's delta, and it's also going to be theta 2 for the second refraction situation. Now, maybe a harder one along here is to say, okay, what is this incident angle? And maybe to figure that out, I need to draw this ray back to where it hit here. Okay. Which you can look back on this picture, but you can see that's the 19.6. So the 19.6 is also the incident angle coming into the second interface. And so that's because this, which is 19.6, these are alternate interior angles for parallel lines. And so we got to use our geometry here to go, okay, what is that incident angle? And so I'm going to remember that parallel lines, alternate interior angles are equal. So again, using this 19.6, I've got an incident angle right here, same as this deviation angle in the first interface is 19.6. So now if I apply Snell's law to this second and last case, I could say it's starting in the glass, so this is 1.65. It is then entering at an angle of 19.6. It's going into the air, so n is equal to 1. And then that'll give me theta 2, which, as I mentioned, theta 2 is also going to be my deviation angle. And so, like I said, the setup here made it a little nice that these were the same and these were the same. That cut down on a lot of geometry. There was still already a lot of geometry, but I thought that would be best to cut down on that geometry. Anyway, so finishing the test here, I'm going to say this is 1.65 times sine of 19.6. Then technically divided by 1, which I won't do anything, and then inverse or arc sine gives me an angle of 33.6 degrees. Yay! And that's it. And again, hopefully that one went well for you. But a lot of little details in here, and so a lot of little places that you could have messed up. But hopefully you didn't. But hopefully, if you feel like you didn't get the right answer, maybe it was something minor, like as we talked about in this microscope one, you just got the signs wrong. Or in this case, maybe it was just confusing a little geometry and getting the physics right. That would be a good sign. All right. Hope all this helped, and take care.